The practice is to do round robin style and just go around the room and just read the question and guess at the answer. And then if we don't know it, then we read the explanation associated with it. Sound good for everyone?
It was just me now.
Oh, they disappeared again. Okay.
I was just hoping on listening. But
We can
it's
do
me and you. Let's do this.
the same thing as last night if you want. So
Like, he's in general now? Where's he going? I don't know.
I don't. So first question: what is a crystal lattice filter? A filter with narrow bandwidth and steep skirts made using quartz crystal. B, a filter using lattice-shaped quartz crystals for high Q performance. C, an audio filter made with 4 quartz crystals that resonate at 1 kilohertz intervals. D, a power supply filter made with interlaced quartz crystals. I have no idea, but I'm just going to go with B. And I'm wrong.
I'm thinking C. What's an audio filter used for quartz crystals? Maybe C. Damn. Show us the correct answer.
A.
Deep skips.
Narrow bandwidth and steep skirts. You want to take this one?
What is the maximum bandwidth of data emissions on 60 meters? 1.5 kilohertz, 2.8 kilohertz, 60 kilohertz, 170 kilohertz. I'm gonna go kind of conservative. I'm thinking it's A, 1.5 kilohertz. B.
Yep, B. That's about the standard for single sideband. So it's basically the data that be uh, can be contained within single sideband. It looks like. Yep, with upper sideband data and CW signals. Why are the DIP through-hole package ICs not typically used at UHF and higher frequencies? A, the epoxy coating is conductive above 300 megahertz. B, unsuitable for combining analog and digital signals. C, too many pins. D, excessive lead length. This one is D, excessive lead length. The leads on the DIP chips, I believe they become, because the frequency is so short, the pins on the chips become resonant. Oh, this one. You want to take this one, Frank?
Sure. What is the radiation pattern of two 1/4 wavelengths, vertical antenna spaced a half length lave apart and fed in phase. Um, a figure 8 end along the axis of the array. Hold on, what? I'm trying to go picture this in my head.
I believe the first one is, so if you have two of them, like two towers,
Yeah, I don't think it's a figure 8 because that's not enough to be a figure 8. It's going to be C or D. That's just what I'm feeling.
I'm thinking it's B.
Maybe B.
So it's not, in fire means it's going to go off like straight out from, like in a line from the two towers. And I don't think that's right. Cordial is what I thought it was last time, but I think that's when it's only a quarter wavelength apart. And then I'm not, for some reason, I didn't think it was omnidirectional. But then again, I could have it mixed up again, and this could be the one that we had originally, which is it could be cordial. And I think it's all dependent on how far it's apart. I can't remember. That's the part that I can't remember. So you think it's
It's
C or D? Which one do you want me? Would you like me to pick?
maybe omnidirectional, but I don't really see that being a omnidirectional. It's kind of like it, but um, yeah. All right, I was completely wrong. Of course, because I haven't read any of these or done any studying.
Let's see what they. Okay, so for example, the radiation pattern of two quarter wavelength vertical antennas spaced half wavelength apart and fed 180 degrees out of phase is a figure 8 oriented along the axis of the array. So if it's 180 degrees out of phase, it's along the axis of the array. If the radiation pattern of two quarter wavelength vertical antennas spaced a quarter wavelength apart, fed 90 degrees out of phase, is a corduroid, and that is one of the questions because I've seen that question before. And the radiation pattern of two quarter wavelengths spaced half wavelength apart and fed in phase is a figure 8 broadside.
Is that the radiation pattern below?
No, this is
Oh,
E9 2, and they're looking for E9. Oh, that's just areas. Um, if we see the other question, the one on the corduroid,
mm-hmm.
this one, the explanation actually has links to the diagrams, I believe.
Okay.
So we got that like the first day we were testing. We're on the load line of a Class A common emitter amplifier would bias normally be set? A, at the point where the load line intersects the zero basis current curve. B, at the point where the basis resistor equals the load resistor. C, approximately halfway between saturation and cutoff. D, where the load line intersects the voltage axis. Oh, I think it's either D or A. So let's pick A. Nope, and it's not D either. I'm just getting them all wrong. S-
It's not our night.
C, approximately halfway between the saturation and the cutoff. Setting the bias halfway between the saturation and the cutoff gives maximum possible swing in the collective voltage without entering either saturation or cutoff. Okay, you want to take this one?
How is a positive fed supply in a Hartley oscillator? Hartley oscillator?
Hartley, and I don't know what, I haven't heard of that type of oscillator.
Through the link coupler, through a naturalizer capacitor, through a tapped coil, through a capacitor divider. I don't know what a capacitor divider is or a naturalized capacitor. So I know it's not B or D. Through a linked coupler or a tapped. Those are my two guesses.
Let's go with A again. And it's through a tapped coil. Okay. Oh, and uh, if we see that again, I want to go to the remind me to look at the explanation. Which of the following factors determines ground loss for ground mounted vertical antennas operating in the 3 megahertz to 30 megahertz range? A, the standing wave ratio. B, soil conductivity. C, takeoff angle. D, distance from the transmitter.
Takeoff angle. L.
It's talking about ground losses. So,
Well, the takeoff angle means that you're closer to the ground or not. So wouldn't that also increase your ground reflection off the ground and also increase the loss to the ground?
yeah, I'm not exactly sure what they want. I'm going to look at, I'm thinking, yeah, it looks like they're actually talking about like the resistance of the ground itself. High soil conductivity improves ground reflections and ground wave propagation. This is the same effect. This is same effect is also the reason why waves are able to travel very far over large bodies of water.
Okay.
You want to take this one?
I got a call. I got to jump off for a minute here.
Okay. What impedance does an eighth wave transmission line present to a generator when the line is shortened at the far end? A, the same as the characteristics A, the same as the characteristics impedance of the line. B, inductive reactance. C, 0. D, capacitive reactance. And I do not know this one. I am gonna, I believe it's inductive, so I'm gonna guess at B. That is correct. If the far end of the transmission line is a short circuit to, it appears as inductance. If the far end of the transmission line is open, it appears as compactance. What causes intermodulation in an electronic circuit? Not A, too little gain, B, positive feedback, C, nonlinear circuits or devices, D, lack of neutralization. And intermodulation is caused by nonlinear circuits or devices. What is antenna efficiency? A, radiation resistance divided by transmission resistance. B, effective radiated power divided by transmission output. C, total resistance divided by radiation resistance. D, radiation resistance divided by total resistance. I'm going to go with D, radiation resistance divided by total resistance. Hey, we have Steve joining us. You interested in taking this next one, Steve?
I actually already have my extra. I'm just going to drop in and say when you guys are ready to test, let me know, and I'll set you up with a session.
Sounds good. Yeah, we're just going, reading them off and just uh, whether, yeah, you have, if people have their extra or they don't even have general tech, we're just going over and reading them through and uh, guessing at them just to sort of go around the room and stuff. So, but sounds good. Thank you, Steve.
Absolutely.
And this is what is a crystal lattice filter question we've seen before. And that is C, a filter with narrow bandwidth and steep skirts made using quartz crystals. Which of the following describes problems caused by poor dynamic range in a receiver? A, oscillators, instability, and severe audio distortion of all but the strongest received signals. B, cross modulation of the desired signal and insufficient audio power to operate the speaker. C, oscillator instability requiring frequent returning and loss of ability to recover the opposite sideband. D, spurious signals caused by cross modulation. And D, sensitization from strong adjacent signals. I am going to guess a D, spurious signals caused by cross modulation and desensitization. from strong adjacent signals. And that is correct. What is this is a radiation from antenna we've seen already, and that is figure 8 broadside to the axis. And we've seen that one as well. What is inductor saturatization? A, the ability of the inductor's core to store magnetic energy has been exceeded. B, the inductor's voltage rating is exceeded, causing a flashover. C, adjacent inductors become overcoupled. D, inductor windings are overcoupled. And I believe it's A. The ability of the inductor's core to store magnetic energy has been exceeded. Which of the following factors determines ground loss? And that is soil conductivity. Which of the following carrier frequencies is illegal for lower sideband AFSK emissions on the 17-meter band RIDI and data segment of 18.068 to 18.110 megahertz? I believe it is, so it's A 18.110, B 18.6068, C 18.007, D 18.100. And I believe because it's lower sideband, which means it broadcasts on the left side or the lower side of the frequency, B is the illegal frequency because it's at the band edge. So you're actually going to be transmitting off band. Looks like you're back. Are you ready, Frank? Or are you still on call?
I could take some more, but we'll have to go in a bit here. Which of the following HF digital modes use variable length coding for bandwidth frequencies? I don't know what A is. MT63. I heard of Pactor, I heard of RIDI, and PSK31. Um, variable length, bond length. Pactor? B? It's just a guess. Nope.
I'm thinking it's actually ready.
RIDI.
Oh, PSK 31.
Okay.
Yeah, PSK 31 uses variable length coding where the most used characters are given shorter lengths to save bandwidth.
Mm-hmm.
What core
Sorter,
material?
go back. Sorter characters are given less bandwidth. So the bandwidth of the entire data stream is unchanged, but the character have variable bandwidth.
So just like in Morse code, the more popular letters like E, A have shorter um, are shorter. number of
Hmm.
bits. So because because the common characters are used more frequency and they have, say they're only filling 3 bits instead of 6 bits for an E, the overall length of how many bits it takes to do a sentence is less because the common characters have less, require less bits to, um, for what they are. That makes sense, or did I just confuse you more?
That makes sense, but I thought it was a variable because the data rate, the baud rate.
Oh,
I was thinking,
no, it's the data length to for the character per character is
okay, so
variable.
I got confused.
What core material property determines the inductance of the inductor? A. Permeability. B. Reactivity. C. Thermal impedance. D. Resistance. I believe it's going to be B, and I am wrong. Like most of, let's go with inductance. Let's go with C then. Nope. Last one I pick is permeability, and that is the right answer. And let's see what it says. Permeability is a measure of the response to the given material magnetic to a magnetic field. Okay, I guess it helps when I actually know what the meaning of the word is. I was thinking
Hmm.
I was thinking it was permeability um was something more along the lines of like water set being able to go through a material or something. You want to take this one, Frank?
Which of the following component forms the output of a Class D amplifier circuit? A match load resistor to prevent damage to a switch transistor, a temperature load resistor to improve linearity, a low pass filter to remove switching signal components, a high pass filter to composite for low gain at low frequencies. You got me on this one. I don't know much about amplifiers.
My, I'll, I think would possibly be C or D, just because uh, it's trying to sort of compensate for some of the, in my thinking, it's trying to compensate for some of the drawbacks of a Class D amplifier. Maybe I'm completely
Okay.
wrong in that. So let's pick C. And and my guess was actually correct. A low pass
Low
filter to
pass filter to remove signal components.
switching signal components. Silly memory tip. A D is a low pass grade. Another hint is the word components in question and only answer stem. So components is in both the answer and the question and the answer. Why are received spread spectrum signals resistance to interference. A, if interference is detected by the receiver, it will signal the transmitter to change frequencies. B, the receiver is always equipped with a digital blanker. C, signals not using the spread spectrum algorithm are suppressed in the receiver. D, the high power used by a spread spectrum transmitter keeps its signal from being easily overpowered. My guess is that it's C. Signals not using the spread spectrum algorithm are suppressed in the receiver. And that is correct. Frank, you're
Which
up.
of these felines' impedance would be suitable for constructing a quarter wave Q section for matching a 100 ohm loop to a 50 ohm feedline? 50 ohms, 62 ohms, 75 ohms, and 450 ohms. Off the bat, and I feel like it's a red herring, it's going to be A because the difference is 50.
I think you are right on the fact that it's a red herring.
So at this point, I want to know the math on what makes the right answer the right answer.
I'm trying to think if I can remember what it is before looking at the explanation. Um, I'm gonna go with D. Just and then it's yeah, then 75. When implementing a quarter wave Q section, auto, also known as a quarter wave impedance transformer, the impedance Z of the quarter wave section should be equal to the square root of the impedance of the feed line times the impedance of the loop. In this case, the square root of 50 times 100, which comes to, when you do that math, it comes to
Hmm.
70.71 ohms, and the
See,
closest to that is 75.
when I understand the math, I can answer any question about it instead of just memorizing the answers.
So you times them together and take the square root.
Yep, but this is only for a Q wave quarter wave, right? Or just quarter wave is in generals.
Um, this is doing a quarter wave Q section. Ba- um, yeah, a quarter wave impedance transformer. You want to take this one, Frank?
What is the approximate open circuit voltage produced by a fully illuminated silicone photovoltaic cell? I haven't even heard of that.
It's a solar panel cell.
Okay, 12 volts.
Um, so I will tell you, a whole panel is made up of a whole bunch of small cells.
Okay, so this is a single cell in a solar panel array.
Yes.
So then let's go small, A or C.
So I'll just read off for anyone listening. A,
Oh, you're right. I'm sorry about the audio listeners. A is zero point 0.1 volts. B is 1.5 volts. C is zero point 0.5 volts. D, 12 volts.
so I'll pick C. The other one I'm leaning to is actually it might be B, but you are correct. It is actually C, half a volt per cell. So like when you're looking at some solar panels, they say like 72 cell solar panel. So then it would be 72 times point. And actually, I should know that because I should actually have known the answer because the panels on my roof are 72 cell, and and they produce about in the open open voltage is about 35 volts. So yeah, half a volt per cell. Which of the following HF digital modes uses variable, and we already did this one, PSK31.
Hold on.
Oh, sorry.
Aw. Can you go back one?
No, it's
Probably not.
nope.
I wanted to read the exact wording.
Okay. Uh,
It's okay. It's okay. We'll continue.
okay.
It'll pop up.
What is the effect of al- aliasing on a digital oscilloscope caused by setting the time base too slow? A. Excessive blanking occurs, which prevents display of the signal. B. Calibration of the vertical axis is no longer valid. C. All signals will have a DC offset. D. A false, jittery, low frequency version of the signal is displayed.
Offhandedly, I think it's going to be A.
Okay, let's try A.
Oh,
I was thinking D, that it's gonna be a jittery, it's gonna be a bad jittery signal. And that D is correct. A false, jittery, low frequency version of the signal is displayed.
interesting. I gotta go, man.
Okay, sounds good. Have a good night.
You too now. Catch you later.
Yep. Generally, oscilloscope sampling at 20 megahertz will have filters to eject signals above 10 megahertz for this reason. So we are wrapping it up. Um, Hopefully you enjoyed this study session. Remember to like the videos and to subscribe to my channel. And everyone, please have a good evening or day, whenever you are watching this. Thank you.